Hello again, my curious engineer. Now that you know what Arduino is, we can finally place the Uno beneath our attention and let the board reveal itself, slowly, one part at a time. At first glance, it may look crowded. Blue fiberglass, black chips, silver connectors, rows of labeled sockets, tiny components pressed close together. But nothing here is random. Every visible part supports one of a few needs: power, timing, communication, programming, connection, or protection. And while your eyes move across the board, let the confusion soften. Stay curious, because we will not name everything at once. We will begin at the center, then follow each path outward. This lesson uses the classic Arduino Uno Rev3. At its heart is the Atmega 328P, the same microcontroller we examined before. The board does not replace that chip. It surrounds it with the circuitry needed to power it, reset it, clock it, connect it to a computer, and bring its pins into a form your hands can reach. Think of the Uno as a carefully prepared environment around one small control system. The microcontroller holds the behavior, the board creates the conditions, and as those layers separate clearly in your mind, notice the slight release, the pleasant moment when a crowded surface begins to open and the Uno starts inviting you closer. Begin with the largest black chip on the classic through-hole Uno. This is the Atmega 328P in a 28-pin DIP package. Inside it are the CPU, flash, SRAM, EEPROM, timers, analog measurement hardware, communication interfaces, and the input and output circuitry we explored earlier. Its metal legs do not connect directly to loose wires. The board routes them through copper traces to labeled headers along the edges. A header is a row of sockets where jumper wires, modules, test probes, or expansion boards can make contact. The Uno therefore performs an important translation. Tiny chip legs become larger, stronger, clearly labeled connection points. PB5 becomes Arduino D13. ADC0 becomes Arduino A0. Power and ground appear in dedicated groups. The hidden names remain underneath, but the surface becomes easier to touch. Look closely and you may see thin copper paths moving away from the chip beneath the board's coating. Each trace is an electrical route, a narrow line carrying power or signal from one point to another. One contact leads inward, another carries the response outward, and while the board appears still, imagine those paths becoming active. Follow the signal, small decisions traveling through copper, until code reaches the physical edge of the board and answers through something you can measure, connect, and control. Now let your attention move toward the USB connector. On the official Uno Rev3, this is the large USB Type-B socket. It can provide power, carry uploaded firmware, and exchange serial data with the computer. But the Atmega 328P does not speak USB directly. A second microcontroller, the ATmE GA16U2, sits near the connector and acts as an interpreter. It receives USB communication from the computer and converts it into serial signals used by the Atmega 328P. On many compatible Uno boards, Another chip, such as the Ch.340, performs a similar role. This distinction matters. The large Atmega 328P runs your sketch. The smaller interface chip handles the conversation with the computer. Between them are receive and transmit lines. That is why the board has TX and RX activity LEDs. They flash when data moves through this connection. Brief visible pulses revealing an exchange that would otherwise remain hidden. Follow the path, slowly. Computer, USB cable, connector, interface chip, serial signal. Atmega 328P, one layer translates for the next, and the message moves inward until new firmware reaches flash, or data returns toward the computer. One cable makes contact, the board listens, let the channel open, and through that prepared path, the silent controller becomes ready to receive something new from you. The Uno also needs a stable source of power. The simplest path is through USB. The board can also receive external power through the barrel jack or through VIN. VIN means voltage input. It feeds the board's regulation circuitry rather than behaving like an ordinary signal pin. A voltage regulator reduces a suitable external voltage to the level required by the board. The classic Uno operates mainly with 5-volt logic, and it also provides a limited 3.3-volt output for compatible devices. The power header includes VIN, 5 volts, 3.3 volts, and several GND connections. GND means ground, the shared electrical reference against which other voltages are measured. Two devices exchange signals reliably only when their reference levels are connected correctly. Pause with that idea, find the common point. Because ground is not merely the negative wire, it is the reference that gives every voltage its meaning. 5 volts relative to what? A high signal relative to what? The answer returns to ground. The ON LED shows that the board is powered, but a glowing LED does not prove that every voltage is correct or every connection is safe. Power must enter through an appropriate path, remain within limits, and settle into a stable supply. That steady voltage holds the system quietly open, every circuit ready, every pin waiting, until firmware asks the board to respond. Near the Atmega 328P is the clock component that gives the microcontroller its familiar rhythm. On the Uno Rev3, the main controller normally runs at 16 MHz. That means the timing system provides 16 million clock cycles each second. The CPU and many peripherals use this rhythm to coordinate their work. The clock does not tell the program what to do. It tells the chip when each internal step may proceed. A repeated pulse, a measured interval, a disciplined sequence beneath every instruction. Stay with that rhythm for a moment. Feel the timing. Tension gathered into one pulse, released into the next, again and again. Nearby, you will also find the reset button and reset circuitry. Reset does not erase the firmware. It returns the microcontroller to a defined starting condition and makes the program begin again from its entry point. During an upload, the computer can trigger reset automatically, so the bootloader has a brief opportunity to receive new firmware. When you press the button yourself, current execution stops, lets go of its temporary state, and begins again. The program in flash remains. The working state is rebuilt. The system returns to its beginning. There is something useful in that clean restart. a controlled release of what was happening, followed by the same stored pattern opening once more. The 16 MHz rhythm of the classic Uno is a board choice, not the absolute limit of the Atmega 328P. At a suitable supply voltage, the chip can operate at up to 20 MHz. Historically, Arduino standardized the Uno and Classic Nano around 16, a practical balance of compatibility, timing, and performance. A stock Uno or Nano cannot become a 20 MHz board merely because software declares a larger number. The physical clock source must also provide 20 MHz, while the board definition, core, bootloader, serial timing, delays, and other frequency-dependent code must agree with that reality. With suitable hardware and a correctly configured Arduino core, an Atmega 328P design can run at 20 MHz, gaining roughly 1/4 more clock cycles each second, a modest increase, but sometimes useful when timing margins become tight. Newer AVR boards such as MyTechWaifu and Uno Rev3 use the Atmega 4809, which also supports 20 MHz. Arduino's standard Mega AVR core commonly configures them for 16, but a suitable core and clock setup can use 20. Frequency is not a mystical number beside a board. It is an agreement between silicon, voltage, clock hardware, and software, and when every layer agrees, hold the rhythm, the system can move faster without losing precise timing that keeps each response clean. Along the upper edge are digital pins, D0 through D13. A digital pin works with two logical states, low and high. Firmware can usually configure it as an input to sense a state or as an output to create one. Low is near ground. High is near the board's logic voltage. These names describe valid regions, not perfect mathematical points. Real voltages must still remain within safe ranges. Some pins carry additional functions. D0 and D1 are RX and TX for serial communication with the Atmega 328P. Pins marked with a tilde support hardware, PWM. PWM rapidly switches an output between low and high, so the average effect can control LED brightness, motor power through a driver, and other loads. D13 is connected to the built-in LED, making it useful for simple tests. The labels on the surface are convenient Arduino names. Beneath them remain the Atmega 328P ports, bits, timers, and alternate functions. One pin may therefore be an ordinary digital line, then, after deliberate configuration, become part of serial communication, a timer output, or an interrupt source. Do not memorize every secondary function now. Instead, pause at the row of sockets. Notice the possibilities, a place to sense, a place to answer, a boundary where one careful contact lets the program reach outward and the physical world respond. Along the lower edge are analog inputs, A0 through A5. An analog input can measure a changing voltage rather than reducing it immediately to only low or high. Inside the Atmega 328P, the analog to digital converter turns that voltage into a 10-bit number from 0 to 1023 relative to the selected reference voltage. A 0 through A5 lead to ADC channels. They can read potentiometers, light-sensitive circuits, joysticks, and many other sources that produce a varying voltage. These pins can also be used as digital input or output lines when analog measurement is not required. A4 and A5 have another shared role. They carry SDA and SCL for the two-wire communication interface, commonly called I2C. The Uno also exposes AREF, the analog reference input. It can influence the voltage range used by the ADC, but it must be handled correctly and will be explained later. For now, hold one distinction clearly. Digital input asks, which logical state is present? Analog input asks, how much voltage is present? One gives a decision, the other gives a measured level, and while the same board receives both, let the difference settle. Stay with the sensation of change, because soon your code will learn not only whether the world has moved, but how far, how softly, and with how much intensity. Several smaller features complete the board. The ICSP headers provide direct programming access and expose SPI signals. They can write a bootloader, program a controller without the normal USB upload path, or connect compatible hardware. TX and RX LEDs indicate serial activity. The LLED is tied to D13. The ON LED indicates power. IOREF tells expansion hardware what logic voltage the board uses. Additional SDA and SCL pins repeat the I2C connections in a standard location. Every label promises an electrical role, and every promise has limits. The Uno's pins cannot safely drive motors, relays, heaters, or other demanding loads directly. Those devices need transistors, driver circuits, protective diodes. The 5 volts and 3.3 volts pins are power rails, not ordinary GPIO. VIN is not the same as 5 volts. No pin should receive voltage outside its permitted range. Respecting these boundaries is not caution opposed to creativity. It is what allows contact to remain safe, control to remain precise, and experimentation to continue. Now look at the whole board again. A controller, a USB pathway, power regulation, clock and reset, digital and analog connections, indicators and programming headers. The crowd has become a structure, and in the next lesson, after one quiet look, we will widen the view and compare Uno, Nano, Mega, Micro, and the wider Arduino families.